Alright, so this is section 2.1 if you're looking at your book. What we're talking about here, we're kind of introducing limits at this point. So just to start you off, I'm just going to do a little example here. There we go. Get that out of the way. So S of t is the position function for a rock being thrown upwards. So I'm taking a rock, I'm going to throw it up. It's going to start off really fast, and then when it gets to the very top, it's going to kind of pause for just a split second, and then it's going to come back down and get faster and faster and faster. This is basically what this is showing. So this axis is time. This axis right here is the height. So as we move along in time, the rock gets higher and higher, and then it starts to drop and drop and drop. Okay? So that is the position function, and it's given by this right here. So if you're using this for notes, go ahead, pause the video, and write all this down. So I have a table right here, and I went ahead and I plugged in values for t. So this is my function. So these values, I just replace t. I've got a negative t squared plus 4t. I'm just taking these t values, and I'm replacing t with whatever it is. Okay, so like if I plug in 0, well, negative 0 squared plus 4 times 0 is just 0. So that's where that's coming from, okay? Because this will be helpful later on. So anyway, we have a position function. Now, we kind of start getting into a little bit of calculus here. Let's see if I can kind of move that over just a little bit. It says, what is the average velocity from t equals 0 to t equals 2? So for velocity, if you have a position function, velocity is basically the slope. It's the rate of change. That's what that actually means. So to find that, I just need to find the slope from where t equals 0 up to t equals 2. So basically, I'm looking for a secant line. So your book calls it a secant because it is a secant. A secant goes through the curve at two different places. This is a secant line. All right? So to find that, all I got to do is use something called a difference quotient. This is the formula you use for average velocity. So in the homework, your questions are basically, they're either asking you about average velocity, which is this right here, or instantaneous velocity. That means velocity at a point. And we'll talk about that here in a minute. But let's start with this first. So all you got to do is fill in the formula. So t equals 0, t equals 2. Well, we're going to say that t equals 2. This is basically our t sub 1. T equals 0 is just t sub 0. Okay? So we're just going to plug this stuff in. So I'm going to say, let me move this up here, that the average velocity, let's see, t1 minus t0. Okay, so let's see, that'd be 2 minus 0. That's given to me. S of t1 and S of t0. Okay, so this is basically S of 2 minus, put it like that, S of 0. So I can just look at my table to fill this stuff in because I already made a table. If you don't have a table, you just plug it into your equation right here. Okay. So for my table, I said that S of 2 is going to give me 4 for S of t. Okay, so that's going to be 4 minus, and S of 0 on the table is going to be 0. And on the bottom, I still have 2 minus 0. And if you work this out, you get 2. Now, this is a velocity, so that's distance divided by time. So my distance is in meters, my time is in seconds. So I'm going to say 2 meters per second. Okay? So that would be my average velocity from t equals 0 to t equals 2. Now, there's another thing called instantaneous velocity, and that's asking what's the velocity at a single point. So basically, if you're in a car and you're driving, instantaneous velocity is how fast are you going at any particular point in time. So that's instantaneous. So instantaneous, we have to be a little bit more careful about how we approach it. Instantaneous, so I'm just going to use an example. Let's find the instantaneous velocity at t equals 2. So at this point, it's t equals 2. Now, instantaneous velocity, and I'm going to write this down for you. So instantaneous velocity hopefully I spell this right. So instantaneous velocity at a point, it's always going to be at a single point, is given, move that over, is given by the slope of the tangent line. So instantaneous velocity at a point is given by the slope of the tangent line to that point. So again, if I'm looking at a point right here for instantaneous velocity, well, my tangent line, it's a line that hits this point only once, okay? It doesn't go through this curve twice. It only goes through the curve one time. And you can probably already see this, but my tangent line is going to be just a horizontal line. And the slope of a horizontal line is 0. That means that if I throw the rock up, at this point in time, at the highest point that it reaches, the velocity, which is given by the tangent line, the velocity is 0. So at a single point in time, that rock is perfectly still. But of course, then the time goes on, and the velocity of the rock starts to pick up again, okay? So how do you find instantaneous velocity? Now, I can tell from the picture right here, this is going to be 0. But, I mean, what if it's a different point? What if it's instantaneous velocity at t equals 1? Or t equals 0.25? So we need a way to figure that out. And the way you figure that out is to use an idea called limits. Limits is basically, you have 2 points. What happens at as these points get closer to each other? And so that's what we're going to look at here. So I'm going to make a table. I'll make it down here. And slope. Because velocity is the same thing as our slope. All right, so velocity, slope, rate of change, distance over time, it's the same thing. So let's start with what we know. We know that from 2 to 0, the slope is 2 meters per second. That's my velocity, okay? So 2 meters per second. Now, you're probably wondering, how does that help us? Well, here's the idea. This is the crucial idea here. This secant line, as I move this point closer to this point I want to know the instantaneous velocity. I'm not going to move this point. I want to see what happens as another point gets closer and closer and closer and closer to it. That's the whole idea here. That's much of what calculus is about. What happens as these points get closer and closer together? Because back ever since, 8th grade math, slope of a line, you have to have 2 points, right? Well, instantaneous, I only have 1 point. So what I'm going to do is take 2 points, but move that other point to see how close I can get it. Because if you notice here, as I move that point closer, the tangent line is going to approach, the secant is going to approach my tangent line that I want. So let's try it here. Let's try it from 1 to 2. So from 1 to 2. And I can just, let me show you the table down here. I can just go ahead and use the table that I already made up above here. So I'm going to go from 1 to 2. So you just plug it into the velocity formula. You would just say S S of 1 minus, S of 1 minus S of 0 divided by 1 minus 0. Okay? Well, no, I'm sorry. Yeah, I wrote this down wrong. Oops, my bad. There we go. T1, I'm not going to change. I'm sorry. I'm not going to change T1. Okay, it's T naught that I'm changing. This is the value that's actually going to move. All right, so let me start over here. This would be S of 2 minus S of 1. That would be 2 minus 1 on the bottom. Okay, so that would be your difference quotient. So you plug 2 in for S of t, plug 1 in for S of t, so find the difference, and then find the difference of 2 and 1. Okay, so if you get that, you should end up with 1 meters per second. So again, I know I caused some confusion there for a second here, but again, T1 is the point that I'm fixing. Okay, this is T1. I'm going to call that T sub 1. Okay, it's the other point that I want to move. I want to see what happens as this point moves. All right, so let's go back down here. So T1 is the same. T1 is always going to be 2. I can always leave it as 2. This is the point. So I want to get this closer to this. So let's try 1.5. So if you plug 1.5 in, so I would have S of 2 minus S of 1.5 divided by 2 minus 1.5. I would figure out what that is. And if you figure out what that is, you should get 0.5 meters per second, because we're talking about velocity. Slope is the same as velocity. And then I'm going to get even closer. Let's try 1.9. Well, if you do that, you're going to end up with 0.1 meters per second. Now, some of you might be looking for a pattern here. And so far, it looks like, oh, well, look, if I take T sub 1 and subtract T sub naught, then I get my slope. I get my answer. Well, it usually does not work out that way. I hate to break it to you, but usually it doesn't work that way. You really have to go through these difference quotients. Every time you find a slope, you have to use the difference quotient. But anyway, let's look at what's going on here. If I had 1.999, that's getting even closer. Long story short, you're going to get 0.0001 meters per second. So what is this approaching? This is approaching 0. If I made this 2, so if I made T naught 2, my slope is going to end up being 0. That is instantaneous velocity. You just want to see, what is it approaching? So to find instantaneous velocity, and I'm going to put a little star here. So make the difference between T1 and T naught as small as possible. And I'm going to move that over there. As small as possible. Now, you can't set them equal to each other, because then you get 0. Okay? You can't make it that small. You can't say T1 equals T naught. That's bad. Don't do that. Okay? Just make them as close together as you possibly can, and you will get the instantaneous velocity.